Hello, we are about to review the entire AP Stats course in about 20 minutes. Dot plots are the simplest graphs. Each data value is shown as a dot above its location on a number line. Next, we have stem and leaf plots. A number with the number 6 on the stem and a 1 in the leaf is representative of the number 61. Stem and leaf plots are very good for getting a quick picture of the dataset, but they are not suitable for large datasets. Next, we have histograms. Histograms are commonly confused with bar graphs, but they are not bar graphs, as bar graphs are used to show categorical data, forgot the A on the data, and histograms are shown for quantitative variables. This is how you construct a histogram relating frequency and the length of something in centimeters, corresponding with your data, of course. To construct a box plot, you are going to draw a box from quartile 1 to quartile 3 and draw a line in the middle that represents median, and you're going to draw whiskers that extend to the minimum and maximum that are not outliers, and draw a star for outliers. We will learn how to calculate those things later. When you are describing these distributions, always remember your SOC: shape, outlier, center, and spread. Mean is the most common measure of center calculated by this equation, and it is sensitive to outliers, but the median, the midpoint of the distribution, is not. If the distribution is skewed right or left, use median over mean. A distribution with extra numbers on the right side of the median is going to be considered skewed right, and a distribution with extra numbers on the left side of the median is going to be considered skewed left. This is a measure of spread, and this is calculated by taking the smallest number subtracted from the largest number. Range is sensitive to outliers, but IQR is not. Q1 is the median of the numbers left to the median, and Q3 to the right. Outliers are calculated by both of these two equations shown here. Standard normal curve is a distribution with a mean of 0 and a standard deviation of 1. To standardize a variable to a normal curve, you calculate its z-score. Summary of a distribution is minimum Q1, median, Q3, max. And subtracting by a constant shifts the distribution center and location, whereas multiplying and dividing by a constant changes center, location, and spread. Again, you always gotta remember your SOCs. Comparing spread, always use explicit terms like greater than or less than. When comparing shape, use the words unimodal, bimodal, and multimodal to describe the amount of peaks in the distribution, as well as noting outliers, unusual figures, and clusters and gaps. For essentially, remember to compare median to get an accurate representation of all types of data.
Probability model describes chance behavior by listing possible outcomes. An event is a subset of the possible outcomes in a sample space. The probability of an event happening can be displayed through a decimal, in which probability of event A is between 0 and 1. In order to calculate P of A, you must divide number of outcomes corresponding to event A by total number of outcomes in a sample space. In addition to this calculation, you can also find P prime of A, which is the chance that the event does not happen. Separate events A and B are mutually exclusive or disjoint if they have no outcomes in common. Frequency is the count of individuals that fall within each category, whereas relative frequency is the percent of individuals that fall within each category. Pie charts and bar graphs display distributions of categorical data, like this. A two-way table summarizes information by graphing outcomes in categories. Association occurs between two variables if knowing the value of one variable helps determine the value of the other. A scatterplot displays the relationship between two quantitative variables on the same individuals, each individual representing 1 point on the graph. The x-axis represents the explanatory variable, and the y-axis represents a response variable. In a scatterplot, you can determine direction, which is a positive versus negative association, form, which could be a linear, cluster, or curve arrangement, and lastly, strength, which is how close the points lie to a simple form line. An R-value can be used to determine strength and direction of a linear association. This is only for straight line relationships. An R-value greater than 0 is a positive correlation, and an R-value less than 0 is a negative association. All R-values are between -1 and 1. A perfect correlation would be an R-value of plus or minus 1. Always remember, correlation does not imply causation. A regression line shows how a response variable changes as an explanatory variable changes, or predict a value of y for any value of x. The equation y hat equals a plus bx is used, where slope is b, y-intercept is a, and a predicted response is y hat. Residuals show differences between observed and predicted values of y. For any value of x, the residual shows the difference between any observed y value and a predicted y value determined from the regression line. Standard deviation of a residual shows the typical size of prediction errors.
Interpreting probability, including long-run frequency interpretation. Chance behavior is unpredictable in the short run but has a regular and predictable pattern in the long run. Law of large numbers concept. If we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. A coin can be flipped 2 times and land on heads both times, but after 100 flips, the proportion will be close to 0.5. The more trials there are, the more regular a pattern becomes. Addition rule, multiplication rule, conditional probability, and independence. Addition rule is that for mutually exclusive events, the probability of A or B equals the probability of A plus probability of B. And remember to subtract the probability of A and B if they aren't mutually exclusive. General multiplication rule is that the probability of A and B equals the probability of A times the probability of B given A. The last part is the conditional probability. The probability of A given B equals the probability of A and B minus the probability of B. The probability that one event happens given another has already happened. 2 events are independent if the occurrence of one doesn't change the probability that the other will happen. If the events are independent, the probability of A given B equals the probability of B. Discrete random variables and probability distributions. Binomial and geometric. A discrete random variable is a variable with a countable number of values adding up to 1. An example is the number of marbles in a jar or a student's grade level. A continuous variable would be a measurement such as height of a person or time it takes to drive a distance. Binomial settings have a fixed set of n trials, and geometric setting counts the number of trials until an event of interest happens. Simulation of random behavior and probability distribution. A simulation is an imitation of chance behavior, most often carried out with random numbers. Follow the 4-step plan. State the question of interest, plan how to use a chance device to imitate a process, do many repetitions, and make a conclusion based on the results. Mean and standard deviation, linear transformation. Mean is a measure of center and spread is usually identified by standard deviation. A linear transformation does not change the shape unless you multiply by a negative number, but can change the center and spread depending on the type of transformation. Multiplying or dividing each value of the random variable by a positive constant b multiplies or divides the mean and standard deviation by b. Adding a constant a to subtracting a constant a from each value of the random variable adds a to or subtracts a from the mean but does not change the standard deviation.
Some properties of normal distributions include the mean equaling the median in the center of the graph, a symmetrical bell-shaped unimodal density curve above the horizontal axis, with an area under the curve being 1. The mean is equal to 0 and the standard deviation is equal to 1. There is also the 68, 95, 99.7 rule. One standard deviation of the curve is 68% of the area. Within 2 standard deviations is 95%, and within 3 is 99.7% of the area. There are also skewed distributions. Skewed to the left means the tail is to the left, along with the mean. And skewed to the right means the tail is to the right, along with the mean. You can use the table to find the area under a curve from a certain point. Let's say you want to find the area under the curve to the left of z equaling 0.81. The 68, 95, 99.7 rule would be tough to use. You can instead use a table for this. I find 0.8 and 0.01 to make 0.81, and the number where they intersect is the area to the left of the point 0.81. If I want the area to the right of 0.81, I go 1 minus 0.7910. We can answer a question about areas in any normal distribution by normalizing and using the tables or technology. We can also tell how well the data would follow a linear plot line. You can also use the same equations, tables, and calculator technology on all normal and approximately normal graphs. If knowing whether any event involving x alone has occurred tells us nothing about the occurrence of any event involving y alone and vice versa, then x and y are independent random variables. So basically, independent means 2 events are unrelated, such as buying a coat and the toppings on your pizza. Dependent means 2 events are related, such as robbing a bank and going to jail. When adding 2 random variables x and y, the mean is the mean of x plus the mean of y, and the standard deviation is the standard deviation of x squared plus the standard deviation of y squared all over under the square root. When subtracting 2 random variables x and y, the mean is the mean of x minus the mean of y, and the standard deviation is the same, but instead of standard deviation of x plus y, it is the standard deviation of x minus y. These are only correct if x and y are independent. Also, if x and y are normally distributed, then x plus y and x minus y are too. When a problem involves both linear transformations and a combination of random variables, do the linear transformations first.
Sampling distributions. What are they? Well, they show every possible result a statistic can take in every possible sample from a population and how often each result happens, which can tell us how trustworthy the statistic is as an estimate of the parameter and really the probability of distribution of a given statistic based on a random sample. This generally is described using the SOX acronym: shape, outliers, center, and spread. So an example of a sample distribution is if we took 20 kids out of the school and took their average height of that sample, that would be 1 point. And if we took a ton of samples of 20 and took the averages of all of them, then we'd have a sample distribution. Now let's talk sampling distributions of proportions. A proportion is basically how many out of the whole sample do the thing. Like how many students from our first sample like ice cream. So if we take this proportion many times, we will get the sample distribution, and this will tell us how good the statistic p hat is as an estimate of the parameter. Once we have our sample distribution, we will find the mean and the standard deviation. To find the standard deviation, use the equation square root of p times 1 minus p over n, as long as the 10% condition is satisfied. As n, the sample size, gets bigger, the standard deviation will get smaller and the distribution becomes more normal. Find the mean, which is actually the true value of p, which, if it equals to the population proportion, means it is an unbiased estimator of p. Sampling distributions of a sample mean. The mean is used more often with quantitative data, where proportion is categorical data. Mean sample distribution is very similar to the proportion to sample distribution. You want to find the mean and standard deviation. The equation for standard deviation of a sample mean here is standard deviation over square root of n as long as the 10% rule is satisfied. The sample mean is always an unbiased estimator of the population. This is because the central limit theorem, which says when the n is large, the sample distribution is approximately normal. This helps us know if we need a bigger sample size, because if it's not normal, then the sample was too small. Okay, sampling distributions of a difference between two independent sample proportions. This is used to compare a specific characteristic of two separate populations. To compare them, do an SRS with an independent size n. Then find shape, center, and spread. Shape will be normal when all of these are at least 10. Center, aka mean, can be found using this equation. And finally, spread, aka standard deviation, can be found using this equation as long as the 10% rule is satisfied. Now, sampling distributions of a difference between two independent sample means. Same ideas with proportions, you want to get the shape, center, and spread. Shape. So if the population distributions are normal, this will also be normal, or it will be normal if both samples are over 30. Center, aka mean, is just mean 1 minus mean 2 of the samples. Spread, the standard deviation, can be found using this equation as long as the 10% rule is satisfied. So if we don't know the standard deviation, then we use a t-distribution. This is always unimodal, symmetric, and centered at 0. The higher the degrees of freedom, the closer to the normal curve. There is also a t-distribution for every positive degree of freedom found by n minus 1. This works only if the sample is normal or large and satisfies the 10% rule. It can then be used to find percent confidence interval. Okay, and lastly, chi-squared distribution is how far the observed counts are from the expected counts. X squared equals the sum of observed minus expected squared over expected. Due to this, the sample must be random and a size of at least 5. High chi-squared is evidence against HO and for HA.
So when we conduct a confidence interval, what we are saying is that we are blank % confident that the interval blank to blank captures the true proportion or mean of a given context. So let's say we have 25 trials and it's a 95% confidence interval. So we have all of these intervals and 24 of them will contain the true population mean. What we have is a point estimate plus or minus critical value times the standard error. So we're going to have our point estimate, which is our statistic or our sample proportion or mean, and then we have plus or minus our margin of error, so we get an interval. Next, what we're going to do is we're going to use this little acronym, PANIC, stands for parameters, assumptions, name intervals and variables, interval calculations, and conclusion and context. So what we're going to do is we're just going to work right through it. So we've got parameters. So let P be the true proportion of blank and let mu be the true proportion of blank. So what you're going to put in here is the context of the problem, saying like the number of, like the proportion of students that got the question right. And so if you have if you're comparing the difference between two proportions or the difference between two means, you have to state P1 and P2 and then mu1 and mu2. Next, you go to assumptions. For your proportions, you're going to say it's random and normal. Also, if it's more than one proportion, you're going to say it's independent. It's the same for means, random and normal. You just have to say that n is greater than or equal to 30, and then np is greater than or equal to 10, and then n1 minus p is greater than or equal to 10. For all of these, you have to state why. So you have to say that it's a simple random sample because it says it's a simple random sample. And for this, you have to say that you have to put in the specific numbers and prove. Next, you're naming your intervals and your variables. If you have a one sample z interval for p, you're using this equation p hat plus or minus the z star, square root of p hat 1 minus p hat over n. You label your variables, and then you do the same thing, and then you solve. And then do the same thing over here. One sample t interval for you, or for mu, you have your sample mean plus or minus your t star as of x over n. So this is a standard deviation. This is your square root of your sample size. And so if you have two samples or two for proportions or for means, you use these two equations here. Next, also, when you're calculating for your critical values, you use inverse norm for your z star and your inverse t for your t star. And when you're doing your confidence intervals, if it's a 0.95, if it's a 95% confidence interval, you have to say that it's 0.95 plus this 0.025. It's all of this area under here, so it's actually a 0.975 when you put it into the calculator. Your degrees of freedom is n-1, and your standard deviation and all that stuff for the z-score is 0 and 1. And so then you have your conclusion in context. You say we are blank % confident that the interval blank to blank captures the true proportion of blank. And we are blank % confident that the interval blank to blank captures the true mean of blank. If you have two proportions or two means, you just say it captures the true difference in proportions or the true difference in means. Next, calculated commands: 1 prop z interval, 2 prop z interval, inverse norm, t interval, 2 sample t interval, inverse t. If you're doing linear regression, you're going to get a calculator printout or computer printout. So this is your sample mean, and this is your sample standard deviation, or your sample slope. And so what we're going to do is you're going to do panic. You're just going to say let b be the true slope for population regression line for predicting y from x. You have linear, linear, independent, normal, equal variance, and random. And then you have your one sample t interval for b. It's b plus or minus the t star and the standard error. So b is your sample slope, t star is your t star from inverse t, and then your standard error, which they will usually give you. Calculate, you say we are blank % confident that the interval blank to blank captures the true population slope of the regression line that predicts blank from blank.
Significance testing is a way you choose between two hypotheses, which are usually statements about the mean or the proportion of a population. Start off with a null hypothesis, H0, which is the hypothesis that we are looking to debunk. The alternative hypothesis, HA, is a claim that we want to be true. Once a significance test is done, you will get a p-value that will be either above or below the critical value, which is most often 0.05. If the p-value is above the critical value, then you must fail to reject the null. But if it is below the critical value, you must reject the null. A one-sided test looks for an overstatement or an understatement, while a two-tailed significance test will look for any difference from the expected value. Errors happen when our conclusions are incorrect. Rejecting the null when it is really true is a type 1 error. Failing to reject the null when the alternative is true is a type 2 error. Power is the probability of a type 2 error occurring. When significance testing, first, state the parameters, state your hypothesis, make sure that the data fits all of your assumptions, and check the conditions, and then you are free to begin testing. When testing, plug given values into one of these 8 equations or calculator functions. For the 1 sample z test and the 2 sample z test, this will give you an inference about proportions. For the 1 sample t test and the 2 sample t test, this will give you an inference about means. And for the linear regression t-test, this will give you an inference about the relationship between two slopes. The chi-square goodness of fit and the chi-square test for homogeneity will give you an inference about the distribution of categorical variables, and the chi-square test for independence will give you an inference about the relationship between two categorical variables. Finally, make a decision based on your tests, stating the conclusion while giving context for the problem as a whole.